Hello everyone, it's my honor to participate the Pitch Your Generation Force research competition organized by the GIF Education and Training Working Group. I'm Junlang from Kyushu University. I'm a PhD student currently work on the fundamental study on the coolabilities of debris bed based on volumetric heating experiments on spherical magnetic particles. The coolabilities of debris bed is not only an important topic just for the water-cooled reactor, but also for the fourth-generation reactor, including sodium-cooled fast reactor and lead-cooled fast reactor. The debris bed is formed due to the interaction between the coolant and the molten fuel. It is a bunch of irregular particles composed of fused metal oxide and can be considered as the porous medium. Based on the existing experimental result, their diameter is from 0.1 mm to 20 mm. Their characteristic will affect the heat removal and cooling in the core region during the severe accidents of reactor. Basically, the coolability of debris bed is a heat transfer problem between the liquid phase and the solid phase porous medium with volumetric heating. In experiment, there are usually 3 types of heating method for particles, including the bottom heating, resistant elements heating, and induction heating. They all came across some challenges. For example, some of them they are not real volumetric heating. Some of them the contact thermal resistance between the heater and particle is non-negligible, and some of them have the skin effects of non-uniform heating due to the induction heating. Therefore, we need a better heating method to understand the heat transfer characteristic of debris bed with volumetric heating. We therefore propose using direct current heating to heat the metal particles, since the Joule heating effect is volumetric. However, we encounter difficulties at first because the ordinary metal particles have no magnetism and therefore cannot form a stable current path. Finally, the experimental study was successful by using the magnetic particles and pure water to simulate the fuel debris and the liquid phase. The decay was achieved by the direct current heating applied to the magnetic particles. The magnetism ensures the contact pressure between particles and make the volumetric heating possible. The particles are in different sizes, and this may affect the drag force between the two phases as well as the contact areas between the particles. Heat transfer in the system is mainly determined by natural convection and heat conduction, which are related to the characteristics mentioned above. So, which factor is important? We designed several simple control experiments to identify the factors that affect the heat transfer. The first control is to experiment with particles of different size under the same condition. This confirms the effects of particles' diameters on heat transfer. The second control is separate the particles and the water layers with a copper plate with good thermal conductivity. This can confirm the effects of a natural convection between the particle layer and the water layer on heat transfer. And to visualize the flow from the particle beds, we also place the fluorescent dye at the bottom of the bed. In the photo, you could see that the hot flows from the particle bed is visualized under the ultraviolet light by the fluorescent dye, which could help understand the developments of the natural convection in the system. The goal of this study is to understand the heat transfer mode in the debris bed and identify which factor is most important. The convections may occur between the bed and the pool, or just one of them. Based on the current result, it seems that the main contribution of heat removal is by the natural convection inside the pool, which is quite similar to the bottom heating of water. In summary, by direct current heating of magnetic particles, we achieve the volumetric heating like decay heat, and we will figure out the mechanisms of heat transfer for the debris bed. The results of the experiments will serve for the improvements of the heat transfer models and the drag force models of the reactor safety codes, and the numerical simulation for severe accidents analysis of the Generation 4 reactor. Thank you for your attention.